Hello everyone, this is Yu. In this video, I will solve question 2 from homework 10. For this question, we need to collect the definitions of properties of stochastic processes. The first process we need to look at is wide sense stationary process. For this process, its mean equals to a constant, and the autocorrelation of it is a time difference function. That means Rt1, T2 equals to f, the absolute value of the difference between T1 and T2 is tau. And for a little bit of discussion of this process, when we put an input signal, which is a stochastic process, x of t is a WSS process, it's a wide sense stationary process, then it's through a process by a LTI system, we could get the output is also a WSS process. And for the second process, is a independent increment process. For this process, we just need to know the x of T1 minus x of T2 and x of T3 minus x of T4. If they have no overlapping areas, that means they are independent. And the third process we need to see is a Markov process. That means it's a process x of t is a Markov process if the past has no influence on the future when the present is known. Now look at another important process is normal or Gaussian process. That means a process x of t is said to be Gaussian if the random variables x of t, x of t1, x of t2 until x of tn are jointly Gaussian for any n, any t1, t2 until tn, that is fx, the density function of x1, x2 until xn and t1, t2 until tn equals to 1 over the square root of 2 pi to the power of n, the square root times the square root of delta c times e to the power of minus a half times x minus 8 transpose and intervals of c x minus 8. Here is x is the vector of x1 to xn, and capital X is a vector of x t1 to x of tn, and it is equals to the expectation of x, and c is equals to the expectation of x minus 8 times x minus 8 transpose. The fifth process we need to see is the strict sense stationary process. This is a process is static, is not affected by a shift on the time axis. That means strict sense stationary process requires x1 to xn and t1 to tn equals to the density function of x1 to the xn and t1 plus epsilon to the tn times plus epsilon. That condition is very hard to meet. And for the sixth process is white noise. White noise for this process, the winner process W of t if we wish to discuss its derivative of a y of t equals to the derivative of w of t with respect of t, we have the expectation of y of t equals to the conduct the derivative of the expectation of w of t with respect of t is equals to 0, and the correlation of t1 and t2 equals to alpha times delta t1 minus t2. When a process w of t does have the derivative, we use y of t equals to d w of t divided by dt, just a notation. And now let's look at the 7th process. It's mean algorithmic process. We say if the stochastic x of t is a mean algorithmic process if it can meet this condition. If the limitation when t is approaching to infinity 1/2 times t, to do the integral from minus t to t x of t dt is equals to the expectation of x of t in mean square sense, then this process is mean algorithmic process. So for the last one is martingale. For martingale is if we can say a stochastic process x of t is a martingale if the expectation of x of t given by the x of s equals to x1 equals to x1, where for all the s is less or equal than t, then it's a martingale. The conditional for little bit discussion for martingale is the conditional mean equals the condition. This is true for random walk and a winner process. So this is the answer for question 2. Thank you.